Learning objectives. In this chapter, the user will learn the following in detail. Association rule mining. Mining single-dimensional Boolean association rule from transactional database. Mining multi-level association rule. Discussion on few association rule algorithms such as a priori, frequent pattern growth, etc. From association rule to correlation analysis. Introduction. Frequent patterns are patterns that appear frequently in a dataset. A subsequence such as buying first a PC, then a digital camera, and then a memory card, if it occurs frequently in a shopping history database, is a frequent sequential pattern. A substructure can refer to different structural forms such as subgraphs, subtrees, or sublattices, which may be combined with item sets or subsequences. If a substructure occurs frequently, it is called frequent structured pattern. Finding frequent patterns plays an essential role in mining associations, correlation, and many other interesting relationships among data. Moreover, it helps in data classification, clustering, and other data mining tasks. Thus, frequent pattern mining has become an important data mining task and a focused theme in data mining research. A priori algorithm. A priori is a seminal algorithm for mining frequent item sets for Boolean association rules. The name of the algorithm is based on the fact that the algorithm uses prior knowledge of frequent item set properties. A priori employs an iterative approach known as level-wise search, where k item sets are used to explore k+1 item sets. First, the set of frequent 1 item sets is found by scanning the database to accumulate the count for each item and collecting those items that satisfy minimum support. The resulting set is denoted by L1. Next, L1 is used to find L2, the set of frequent 2 item sets, which is used to find L3, and so on, until no more frequent k item sets can be found. The finding of each Lk requires one full scan of the database. To improve the efficiency of the level-wise generation of frequent item sets, an important property called the a priori property is used to reduce the search space. Example. Let's look at a concrete example based on the All Electronics Transaction Database D of below table. There are 9 transactions in this database, that is, modulus of D equals 9. In the first iteration of the algorithm, each item is a member of the set of candidate 1 item sets C1. The algorithm simply scans all of the transactions to count the number of occurrences of each item. Suppose that the minimum support count required is 2, that is, min sup equals 2. Here we are referring to absolute support because we are using a support count. The corresponding relative support is 2 by 9 equals 22%. The set of frequent 1 item sets L1 can then be determined. It consists of the candidate 1 item sets satisfying minimum support. In our example, all of the candidates in C1 satisfy minimum support. To discover the set of frequent 2 item sets L2, the algorithm uses join L1 times L1 to generate a candidate set of 2 item sets C2. C2 consists of modulus of L1 2 item sets. Note that no candidates are removed from C2 during the prune step because each subset of the candidates is also frequent. Next, the transactions in D are scanned and the support count of each candidate item set in C2 is accumulated. The set of frequent 2 item sets L2 is then determined, consisting of those candidate 2 item sets in C2 having minimum support. The generation of the set of the candidate 3 item sets C3. From the join step, we first get C3 equals L2 times L2 equals a number of subsets as shown. Based on the a priori property that all subsets of a frequent item set must also be frequent, we can determine that the 4 latter candidates cannot possibly be frequent. We therefore remove them from C3, thereby saving the effort of unnecessarily obtaining their counts during the subsequent scan of D to determine L3. Note that when given a candidate K item set, we only need to check if its K minus 1 subsets are frequent, since the a priori algorithm uses a level-wise search strategy. The resulting pruned version of C3 is shown in the first table of the bottom row. The transactions in D are scanned to determine L3, consisting of those candidates 3 item sets in C3 having minimum support. The algorithm uses L3 times L3 to generate a candidate set of 4 item sets, C4. Although the join results in the set I1, I2, I3, I5, item set I1, I2, I3, I5 is pruned because of its subset I2, I3, I5 is not frequent. Thus C4 is empty and the algorithm terminates, having found all of the frequent item sets. Join C3 equals L2 join with itself. The results will be as seen on the screen. Prune using the a priori property. All non-empty subsets of a frequent item set must also be frequent. Do any of the candidates have a subset that is not frequent? The 2 item subsets of item set I1, I2, I3 are I1, I2, I1, I3 and I2, I3. All 2 item subsets of item set I1, I2, I3 are members of I2, are members of L2. Therefore, keep I1, I2, I3 in C3. The 2 item subsets of I1, I2, I5 are I1, I2, I1, I5 and I2, I5. All 2 item subsets of I1, I2, I5 are members of L2. Therefore, keep I1, I2, I5 in C3. The 2 item subsets of I1, I3, I5 are I1, I3, I1, I5 and I3, I5. I3, I5 is not a member of L2 and so it is not frequent. Therefore, remove I1, I3, I5 from C3. The 2 item subsets of I2, I3, I4 are I2, I3, I2, I4 and I3, I4. I3, I4 is not a member of L2 and so it is not frequent. Therefore, remove item set I2, I3, I4 from C3. The 2 item subsets of I2, I3, I5 are I2, I3, I2, I5 and I3, I5. I3, I5 is not a member of L2 and so it is not frequent. Therefore, remove I2, I3, I5 from C3. The 2 item subsets of I2, I4, I5 are I2, I4, I2, I5 and I4, I5. I4, I5 is not a member of L2 and so it is not frequent. Therefore, remove I2, I4, I5 from C3. Therefore, C3 equals set I1, I2, I3, I1, I2, I5 after pruning. Algorithm a priori. Find frequent item sets using an iterative level-wise approach based on candidate generation as seen on the screen. Step 1 of a priori finds the frequent 1 item sets L1. In steps 2 through 10, Lk-1 is used to generate candidates of Ck to find Lk for k greater or equal to 2. The a priori general procedure generates the candidates and then uses the a priori property to eliminate those having a subset that is not frequent. Step 3. Once all the candidates have been generated, the database is scanned. Step 4. For each transaction, a subset function is used to find all subsets of the transaction that are candidates. Step 5. The count for each of these candidates is accumulated in steps 6 and 7. Finally, all the candidates satisfying the minimum support in step 9 form the set of frequent item sets L, step 11. A procedure can then be called to generate association rules from the frequent item sets. The a priori gen procedure performs 2 kinds of actions, namely join and prune. In the join component, Lk-1 is joined with Lk-1 to generate potential candidates, step 1 through 4. The prune component, steps 5 through 7, employs the a priori property to remove candidates that have a subset that is not frequent. Generating association rules from frequent item sets. Once the frequent item sets from transactions in a database D have been found, it is straightforward to generate strong association rules from them. This can be done using the equation for confidence. Confidence A implies B equals conditional probability of B given A equals support count of A union B over support count of A. The conditional probability is expressed in terms of item set support count, where support count A union B is the number of transactions containing the item sets A union B, and support count A is the number of transactions containing the item set A. Based on this equation, association rules can be generated as follows. For each frequent item set I, generate all non-empty subsets of I. For every non-empty subsets of I, output the rule S implies I minus S. Support count of I over support count of S is greater than or equal to min confidence, where min confidence is a minimum confidence threshold. Because the rules are generated from frequent item sets, each one automatically satisfies the minimum support. Frequent item sets can be stored ahead of time in hash tables along with their counts so that they can be accessed quickly. Improving the efficiency of a priori. Many variations of the a priori algorithm have been proposed that focus on improving the efficiency of the original algorithm. Several of these variations are summarized as follows. Hash-based technique. Hashing item sets into corresponding buckets. A hash-based technique can be used to reduce the size of the candidate K item sets CK for K greater than 1. For example, when scanning each transaction in the database to generate the frequent 1 item sets L1, we can generate all the 2 item sets for each transaction's hash. That is, map them into different buckets of a hash table structure and increase the corresponding bucket counts. A 2-item set with the corresponding bucket count in the hash table that is below the support threshold cannot be frequent and thus should be removed from the candidate set. Such a hash-based technique may substantially reduce the number of candidate K item sets examined, especially when K equals 2. Figure shows a hash table H2 for candidate 2 item sets. Transaction reduction. Reducing the number of transactions scanned in future iterations. A transaction that does not contain any frequent K item sets cannot contain any frequent K plus 1 item sets. Therefore, such a transaction can be marked or removed from the further consideration because subsequent database scans for J item sets, where J is greater than K, will not need to consider such a transaction. Partitioning. Partitioning the data to find candidate item sets. A partitioning technique can be used that requires just 2 database scans to mine the frequent item sets. It consists of 2 phases. In phase 1, the algorithm divides the transactions of D into n non-overlapping partitions. If the minimum relative support threshold for transactions in D is min sub, then the minimum support count for a partition is min sub into the number of transactions in that partition. For each partition, all the local frequent item sets, that is, the item sets frequent within the partition, are found. A local frequent item set may or may not be frequent with respect to the entire database D. However, any item set that is potentially frequent with respect to D must occur as a frequent item set in at least one of the partitions. Therefore, all local frequent item sets are candidate item sets with respect to D. The collection of frequent item sets from all partitions forms the global candidate item sets with respect to D. In phase 2, a second scan of D is conducted in which the actual support of each candidate is assessed to determine the global frequent item sets. Partition size and the number of partitions are set so that each partition can fit into main memory and therefore be read only once in each phase. The figure shows the mining by partitioning of the data. Sampling. Mining on a subset of the given data. The basic idea of the sampling approach is to pick a random sample S of the given data D and then search for frequent item sets in S instead of D. In this way, we trade off some degree of accuracy against efficiency. The S sample size is such that the search for frequent item sets in S can be done in main memory, and so only a scan of the transactions in S is required overall. Because we are searching for frequent item sets in S rather than in D, it is possible that we will miss some of the global frequent item sets. To reduce this possibility, we use a lower support threshold than minimum support to find the frequent item sets local to S, denoted LS. The rest of the database is then used to compute the actual frequencies of each item set in LS. A mechanism is used to determine whether all the global frequent item sets are included in LS. If LS actually contains all the frequent item sets in D, then only one scan of D is required. Otherwise, a second pass can be done to find the frequent item sets that were missed in the first pass. The sampling approach is especially beneficial when efficiency is of utmost importance, such as in computationally intensive applications that must be run frequently. Dynamic item set counting, adding candidate item sets at different points during a scan. A dynamic item set counting technique was proposed in which the database is partitioned into blocks marked by start points. In this variation, new candidate item sets can be added at any start point, unlike in a priori, which determines new candidate item sets only immediately before each complete database scan. The technique uses the count so far as the lower bound of the actual count. If the count so far passes the minimum support, the item set is added into the frequent item set collection and can be used to generate longer candidates. This leads to fewer database scans than with a priori for finding all the frequent item sets. Association rule mining. Frequent item set mining leads to the discovery of associations and correlations among items in large transactional or relational datasets. With massive amounts of data continuously being collected and stored, many industries are becoming interested in mining such patterns from their databases. The discovery of interesting correlation relationships among huge amounts of business transaction records can help in many business decision-making processes such as catalog design, cross-marketing, and customer shopping behavior analysis. A typical example of frequent item set mining is market basket analysis. This process analyzes customer buying habits by finding associations between the different items that customers place in their shopping baskets. If we think of the universe as a set of items available at the store, then each item has a Boolean variable representing the presence or absence of that item. Each basket can then be represented by a Boolean vector of values assigned to these variables. The Boolean vectors can be analyzed for buying patterns that reflect items that are frequently associated or purchased together. These patterns can be represented in the form of association rules. Measures of interestingness. Support. Confidence. Support. A support of 2% means that 2% of all the transactions under analysis show the computer and antivirus software are purchased together. Confidence. A confidence of 60% means that 60% of the customers who purchased a computer also bought the software. Association rules are considered interesting if they satisfy both a minimum support threshold and a minimum confidence threshold. Let item set I be equal to subsets I1, I2 going on up to IM. Let D, the task relevant data, be a set of database transactions where each transaction T is a non-empty item set such that T is a subset of I. Each transaction is associated with an identifier called a TID. Let A be a set of items. A transaction T is said to contain A if A is a subset of T. An association rule is an implication of the form A implies B, where A is a proper subset of I, B is a proper subset of I, and A is not equal to null, and B is not equal to null, and A intersection B equals null. The rule A implies B holds in the transaction set D with support S, where S is a percentage of transactions in D that contain A union B. This is taken to be the probability P of A union B. The rule A implies B has confidence C in the transaction set D, where C is the percentage of transactions in D containing A that also contain B. This is taken to be the conditional probability P of B given A, that is, support A implies B equals P of A union B. Confidence A implies B equals P of B given A. Rules that satisfy both a minimum support threshold, min sup, and a minimum confidence threshold, min conf, are called strong. A set of items is referred to as an item set. An item set that contains k items is a k item set. The set computer antivirus software is a 2-item set. The occurrence frequency of an item set is the number of transactions that contain the item set. This is also known simply as the frequency, support count, or count of the item set. Note that the item set support defined is sometimes referred to as a relative support, whereas the occurrence frequency is called the absolute support. If the relative support of an item set I satisfies a pre-specified minimum support threshold, then I is a frequent item set. The set of frequent k item sets is commonly denoted by Lk. From the equation we have confidence A implies B equals probability of B given A equals support of A union B over support of A equals support count A union B over support count A. The above equation shows that the confidence of rule A implies B can be easily derived from the support counts of A and A union B. That is, once the support counts of A, B, and A union B are found, it is straightforward to derive the corresponding association rules A implies B and B implies A and check whether they are strong. Thus, the problem of mining association rules can be reduced to that of mining frequent item sets. Association rule mining is a 2-step process. Find all frequent item sets. By definition, each of these item sets will occur at least as frequently as a predetermined minimum support count, min sup. Generate strong association rules from the frequent item sets. By definition, these rules must satisfy minimum support and minimum confidence. Frequent pattern growth. In many cases, the a priori candidates generate and test method significantly reduces the size of the candidate sets, leading to good performance gain. However, it can suffer from 2 non-trivial costs. 1. It may still need to generate a huge number of candidate sets. For example, if there are 104 frequent item 1 sets, the a priori algorithm will need to generate more than 107 candidate 2 item sets. It may need to repeatedly scan the whole database and check a large set of candidates by pattern matching. It is costly to go over each transaction in the database to determine the support of the candidate item sets. An interesting method in this attempt is called frequent pattern growth, or simply FP growth, which adopts a divide and conquer strategy as follows. First, it compresses the database representing frequent items into frequent pattern tree, or FP tree, which retains the item set association information. It then divides the compressed database into a set of conditional databases, a special kind of projected database, each associated with one frequent item or pattern fragment, and mines each database separately. For each pattern fragment, only its associated data set need to be examined. Therefore, this approach may substantially reduce the size of the data sets to be searched, along with the growth of patterns being examined. FP tree construction. Frequent pattern tree construction. First, create the root of the tree, labeled with null. Scan database D a second time. The items in each transaction are processed in L order, that is, sorted according to descending support count, and a branch is created for each transaction. For example, the scan of the first transaction T100, I1, I2, I5, which contains the 3 items I2, I1, I5 in L order, leads to the construction of the first branch of the tree with 3 nodes, I2, support count 1, I1, support count 1, and I5, support count 1, where I2 is linked as a child to the root, I1 is linked to I2, and I5 is linked to I1. The second transaction, T200, contains the items I2 and I4 in L order, which would result in a branch where I2 is linked to the root and I4 is linked to I2. However, this branch would share a common prefix I2 with the existing path for T100. Therefore, we instead increment the count of the I2 node by 1 and create a new node, I4 support count 1, which is linked as a child to I2 support count 2. In general, when considering the branch to be added for a transaction, the count of each node along a common prefix is incremented by 1, and nodes for the items following the prefix are created and linked accordingly. To facilitate tree traversal, an item header table is built so that each item points to its occurrences in the tree via a chain of node links. In this way, the problem of mining frequent patterns in databases is transformed into that of mining the FP tree. Frequent pattern tree mining. Start from each frequent length one pattern as an initial suffix pattern. Construct its conditional pattern base, a sub-database which consists of the set of prefix paths in the FP tree, co-occurring with the suffix pattern. Then construct its conditional FP tree and perform mining recursively on the tree. The pattern growth is achieved by the concatenation of the suffix pattern with the frequent patterns generated from a conditional FP tree. We first consider I5, which is the last item in L rather than the first. The reason for starting at the end of the list will become apparent as we explain the FP tree mining process. The paths formed by these branches are I2, I1, I5, support count 1, and I2, I1, I3, I5, support count 1. Therefore, considering I5 as a suffix, its corresponding two prefix paths are I2, I1, support count 1, and I2, I1, I3, support count 1, which forms its conditional pattern base. Using this conditional pattern base as a transaction database, we build an I5 conditional FP tree which contains only a single path, I2 support count 2, I1 support count 2. I3 is not included because its support count of 1 is less than the minimum support count. The single path generates all the combinations of frequent patterns, I2, I5 support count 2, I1, I5 support count 2, I2, I1, I5 support count 2. For I4, its two prefix paths from the conditional pattern base, I2, I1 support count 1, I2 support count 1, which generates a single node conditional FP tree, I2 support count 2, and derives one frequent pattern. Similar to the preceding analysis, I3's conditional pattern base is I2, I1 support count 2, I2 support count 2, I1 support count 2. Its conditional FP tree has two branches, I2 support count 4, I1 support count 2, and I1 support count 2, which generates the set of patterns I2, I3 support count 4, I1, I3 support count 4, I2, I1, I3 support count 2. Finally, I1's conditional pattern base is I2 support count 4 with an FP tree that contains only one node, I2 support count 4, which generates one frequent pattern, I2, I1 support count 4. The FP growth method transforms the problem of finding long frequent patterns into searching for shorter ones in much smaller conditional databases recursively and then concatenating the suffix. It uses the least frequent items as a suffix, offering good selectivity. The method substantially reduces the search costs. When the database is large, it is sometimes unrealistic to construct a main memory-based FP tree. An interesting alternative is to first partition the database into a set of projected databases and then construct an FP tree and mine it in each projected database. This process can be recursively applied to any projected database if its FP tree still cannot fit in main memory. A study of the FP growth method performance shows that it is efficient and scalable for mining both long and short frequent patterns and is about an order of magnitude faster than the a priori algorithm. Frequent pattern growth algorithm. Mine frequent item set using an FP tree by pattern fragmented growth. Input D, a transaction database, the minimum support count threshold. Output, the complete set of frequent patterns. Method. The FP tree is constructed in the following steps. Scan the transaction database D once. Collect F, the set of frequent items and their support counts. Sort F in support count descending order as L, the list of frequent items. Create the root of an FP tree and label it as null. For each transaction, trans in D, do the following. Select and sort the frequent items in trans according to the order of L. Let the sorted frequent item list in trans be P or P, where small p is the first element and capital P is the remaining list. Call insert tree P or P, T, which is performed as follows. If T has a child n such that n item name equals P item name, then increment n count by 1. Else create a new node n and let its count be 1. Its parent link be linked to T and its node link to the nodes with the same item name via the node link structure. If P is non-empty, call insert tree P, N recursively. The FP tree is mined by calling FP growth, FP tree null, which is implemented as seen. Mining frequent item sets using the vertical data format. Both the a priori and FP growth methods mine frequent patterns from a set of transactions in TID item set format, that is, TID item set, where TID is a transaction ID and item set is a set of items bought in transaction TID. This is known as a horizontal data format. Alternatively, data can be presented in item TID set format, that is, item TID set, where item is an item name and TID set is a set of transaction identifiers containing the item. This is known as a vertical data format. Mining close and max patterns. A naive approach would be to first mine the complete set of frequent item sets and then remove every frequent item set that is a proper subset of and carries the same support as an existing frequent item set. However, this is quite costly. Pruning strategies include the following. Item merging. If every transaction containing the frequent item set X also contains an item set Y, but not any proper superset of Y, then X union Y forms a frequent closed item set and there is no need to search for any item set containing X but no Y. Sub-item set pruning. If a frequent item set X is a proper subset of an already found frequent closed item set Y and support count X equals support count Y, then X and all of X's descendants in the set enumeration tree cannot be frequent closed item sets and thus can be pruned. Item skipping. In the depth first mining of closed item sets, at each level there will be a prefix item set X associated with a header table and a projected database. If a local frequent item P has the same support in several header tables at different levels, we can safely prune P from the header tables at higher levels. When a new frequent item set is derived, it is necessary to perform two kinds of closure checking. Superset checking, which checks if this new frequent item set is a superset of some already found closed item sets with the same support, and subset checking, which checks whether the newly found item set is a subset of an already found closed item set with the same support. A compressed pattern tree can be constructed to maintain the set of closed item sets mined so far. The pattern tree is similar in structure to the FP tree, except that all the closed item sets found are stored explicitly in the corresponding T branches. For efficient subset checking, we can use the following property. If the current item set SC can be subsumed by another already found closed item set SA, then SC and SA have the same support. The length of SC is smaller than that of SA, and all of the items in SC are contained in SA. Based on this property, a two-level hash index structure can be built for fast accessing of the pattern tree. The first level uses the identifier of the last item in SC as a hash key, since this identifier must be within the branch of SC, and the second level uses the support of SC as a hash key, since SC and SA have the same support. From association rule to correlation analysis. From association analysis to correlation analysis. The support and confidence measures are insufficient at filtering out uninteresting association rules. To tackle this weakness, a correlation measure can be used to augment the support confidence framework for association rules. This leads to correlation rules of the form A implies B, support, confidence, correlation. That is, correlation rule is measured not only by its support and confidence, but also by the correlation between item sets A and B. There are many different correlation measures from which to choose. Lift is a simple correlation measure that is given as follows. The occurrence of item set A is independent of the occurrence of item set B. If probability of A union B equals probability of A into probability of B. Otherwise, item sets A and B are dependent and correlated as events. This definition can easily be extended to more than two item sets. The lift between the occurrence of A and B can be measured by computing lift A and B equals probability of A union B over probability of A, probability of B. If the resulting value of above equation is less than 1, then the occurrence of A is negatively correlated with the occurrence of B, meaning that the occurrence of one likely leads to the absence of the other one. If the resulting value is greater than 1, then A and B are positively correlated, meaning that the occurrence of one implies the occurrence of the other. If the resulting value is equal to 1, then A and B are independent and there is no correlation between them. Above equation is equivalent to probability of B given A over probability of B, or confidence A implies B over support B, which is also referred to as a lift of the association or correlation rule A implies B. In other words, it assesses the degree to which the occurrence of one lifts the occurrence of the other. For example, if A corresponds to the sale of computer games and B corresponds to the sale of videos, then given the current market conditions, the sale of games is said to increase or lift the likelihood of the sale of videos by a factor of the value returned by the above equation. Mining. Multi-level association rule. Items often form hierarchy. Items at the lower level are expected to have lower support. Rules regarding item sets at appropriate levels could be quite useful. Transaction database can be encoded based on dimensions and levels. We can explore shared multi-level mining. Approach. A top-down progressive deepening approach. First, find high-level strong rules. If a person buys milk, he also buys bread with a support percentage of 20 and a confidence level of 60%. Then find the lower level weaker rules. 2% of the people buying milk also buy wheat bread with a support level of 6% and confidence of 50%. Variations at mining multiple level association rules. Level cross association rules. 2% of the people buying milk also buy Wonder wheat bread. Association rules with multiple alternative hierarchies. 2% of the people buying milk also buy Wonder bread. 2 multiple level mining association strategies. Uniform support, reduced support. Uniform support. The same minimum support for all levels. One minimum support threshold. No need to examine item sets containing any item whose ancestors do not have minimum support. Drawback. Lower level items do not occur as frequently support threshold. Too high gives miss low-level associations. Too low gives generate too many high-level associations. Level 1, minimum support is 5%. Level 2, minimum support is 5%. Reduced support. Reduced minimum support at lower levels. There are 4 search strategies: level by level independent, level cross-filtering by k item set, level cross-filtering by single item, controlled level cross-filtering by single item. Level by level independent, full breadth search, no background knowledge is used, each node is examined regardless of the frequency of its parent. Level cross-filtering by single item. An item at the ith level is examined if and only if its parent node at the i-1th level is frequent. Level cross-filtering by k item set. A k item set at the ith level is examined if and only if its corresponding parent kth item set at the i-1th level is frequent. This restriction is stronger than the one in level cross-filtering by single item. There are not usually many k item sets that, when combined, are also frequent. Many valuable patterns can be mined. Controlled level cross-filtering by single item. A variation of the level cross-filtering by single item relaxes the constraint in this approach. Allow the children of items that do not satisfy the minimum support threshold to be examined if these items satisfy the level passage threshold. Level passage support. Level passage support value. It is typically set between the min support value of the given level and the min support of the next level. Level 1, min support is 12%. Level passage support is 8%. Level 2, min support is 4%. Redundancy filtering. Some rules may be redundant due to ancestor relationships between items. Definition: a rule R1 is an ancestor of a rule R2 if R1 can be obtained by replacing the items in R2 by their ancestors in a concept hierarchy. Example: R1, milk gives wheat bread, support 8%, confidence 70%. R2, 2% milk gives wheat bread, support 2%, confidence 72%. Milk in R1 is an ancestor of 2% milk in R2. We say the first rule is an ancestor of the second rule. A rule is redundant if its support is close to the expected value based on the rule's ancestor. R2 is redundant since its confidence is close to the confidence of R1, kind of expected, and its support is around 2% equals 8% of quarter. Rule 2 does not add any additional information. Mining single-dimensional association rules from transactional database. In this section, we will learn methods for mining the simplest form of association rules, single-dimensional, single-level. Then methods for mining association rules that, unlike a priori, do not involve the generation of candidate frequent item sets. The a priori algorithm, finding frequent item sets using candidate generation. A priori is an influential algorithm for mining frequent item sets for Boolean association rules. The name of the algorithm is based on the fact that the algorithm uses prior knowledge of frequent item set properties. A priori employs an iterative approach known as a level-wise search, where f item sets are used to explore k plus 1 item sets. First, the set of frequent 1 item sets is found. This finding of each LK requires one full scan of the database. To improve the efficiency of the level-wise generation of frequent item sets, an important property called the a priori property is used to reduce the search space. In order to use the a priori property, all non-empty subsets of a frequent item set must also be frequent. This property is based on the following observation. By definition, if an item set, that is, I union A, cannot occur more frequently than therefore I union A is not frequent either, that is, probability of I union A is less than min sub. This property belongs to a special category of properties called anti-monotone, in the sense that if a set cannot pass a test, all of its supersets will fail the same test as well. It is called anti-monotone because the property is monotonic in the context of failing a test. To understand how the a priori property is used, let us look at how Lk-1 is used to find Lk. A two-step process is followed, consisting of join and prune actions. The join step. The set of candidates k item sets, element of Lk, Ck, is generated by joining Lk-1 with itself. Lk-1 join Lk-1. Given L1 and L2 of Lk-1, Li equals Li1, Li2 going up to Lik-1. Similarly, Lj equals Lj1, Lj2, Lj3 going up to Ljk-1, where Li and Lj are sorted. Li and Lj are joined if there are different, no duplicate generation. Assume the following. Li1 equals Lj1, Li2 equals Lj2 going up to Lik-2 equals Ljk-2, and Li of k-1 is less than Ljk-1. The resulting item set is Li1, Li2, Li3 going up to Lik-1, Ljk-1. Example of candidate generation. L3, ABC, ABD, ACD, ACE, BCD. Self-joining. L3 joins L3. ABCD from ABC and ABD, ACDE from ACD and ACE. Prune step. Ck is a candidate item set of size k, which is a superset of Lk. Implies some item set in Ck may or may not be frequent. Lk, that is a frequent item set of size k, test each generated item set against a database. Scan the database to determine the count of each generated item set and include those that have a count no less than the minimum support count. This may require intensive computation. Use a priori property to reduce the search space. Any k-1 item set that is not frequent cannot be a subset of frequent k item set. Remove from Ck any k item set that has a k-1 subset not in Lk-1 item sets that are not frequent. Efficiently implemented. Maintain a hash table of all frequent item set. Example of candidate generation and pruning. L3 equals ABC, ABD, ACD, ACE, BCD. Self-joining. L3 joins L3. ABCD from ABC and ABD, ACDE from ACD and ACE. Pruning. ACDE is removed because ADE is not in L3. C4 equals ABCD. Conclusion. In this chapter, we have covered the following in detail. Association rule mining. Mining single-dimensional Boolean association rule from transactional database. Mining multi-level association rule. Discussion on few association rule algorithms such as a priori, frequent pattern growth, etc. From association rule to correlation analysis.